Welcome to this video on magnitude-based inference. My name is Bas van Horen and I'm a pre-PhD student at Maastricht University, Department of Nutrition and Movement Sciences. In this presentation, I will discuss magnitude-based inference, which is a statistical method that is frequently used in sports science and sports medicine and also increasingly in other fields to make inferences about the effects in a population from a sample. In this video, I will first explain how the method works, and in the second video, I will present some critique on the method. Before I start, I would like to note that I'm no statistician, but rather a sports scientist with an interest in how we can draw objective conclusions based on data and numbers. Some slides I use have been made by Will Hopkins, who is the developer of magnitude-based inference and can be found on sportsci.org. I will first present magnitude-based inference as proposed by the developers of this method, regardless of whether that is indeed fundamentally correct, so you will understand how the method works. In the second video, I will discuss some critique on magnitude-based inference and responses to the critique so you can decide on whether you think the method is appropriate to use. Before I start explaining magnitude-based inference, I will briefly provide some background information on why we need statistical inference in the first place and why magnitude-based inference was developed. Usually in sports science or sports medicine, and also many other fields, we would like to know the effects of an intervention for a very large sample or population. For example, the effects of caffeine intake on repeated sprint performance in all male soccer players between 18 and 35 years, or the difference in fatigue during walking between all female patients with cardiovascular disease and no cardiovascular diseases. But when we do a study, we usually only have a small sample, which may or may not be randomly selected from the population. For example, we only have a group of 20 football players or only 15 female patients with cardiovascular diseases. We do a study with the sample, find an effect, and are then interested if this effect also applies to a larger group, the population. We use statistical inferential methods in an attempt to say something about the effect in the population. There are many ways to make statistical inferences. The most commonly used one in sports science and sports medicine is probably null hypothesis significance testing, in which you formulate a null hypothesis of no effect and try to disprove it. P-values are frequently used to assist in making inferences for this method, with a p-value smaller than 0.5 or 0.01 often being used to indicate that the result is statistically significant, which essentially means this is a surprising finding if we assume that there is no true effect. There are, however, various problems with null hypothesis significance testing and p-values specifically, and this approach has therefore been heavily criticized for decades. The most common criticism is that large samples can sometimes lead to significant results that are not practically relevant. Conversely, small sample sizes can fail to get significant results that may actually be practically relevant. We will come back to this later. Second, the p-value is generally used in a dogmatic and arbitrary fashion and has grown into something nonsensical. If a p-value is 0.051, then the result is insignificant and it is frequently concluded that the intervention is not effective or there is no difference between the groups. However, if one data point is added, causing a drop to a p-value of 0.049, then the result is suddenly significant and the intervention is said to be effective. This is a 180-degree change in the conclusion based on just one participant or data point. If the null hypothesis is rejected based on the p-value passing a predetermined threshold, it is said that the true difference could not be zero or not a specific value. So if it isn't zero or the other specified value, then what is the difference? How large is it? Is it clinically relevant? We don't want to know what it isn't, but what the difference is. The p-value doesn't really provide an answer to this question. It has also been argued that null hypothesis testing uses two methods which are fundamentally incompatible, but I won't discuss these issues in more detail here. Finally, there are many misinterpretations of p-values and null hypothesis testing, like a p-value of greater than 0.5 means no effect, or there is a result that is not publishable. And as a result, some researchers unfortunately perform p-hacking, which essentially is analyzing the data in many ways until you find a significant effect. In other words, if you torture the data long enough, it will confess and provide a significant result. Based on the problems, more and more people, including statisticians, are suggesting that we should stop using p-values and perhaps null hypothesis significance testing altogether. But you may think, surely p-values can't be that bad if almost all researchers are using them, right? Why would they otherwise be using them? Well, they are using it because it's a vicious circle. Schools teach null hypothesis testing because journals and editors want it. Editors and journals want it because they have been taught it in college or grad school, and this just keeps going on. So it is hard to get rid of p-values and hypothesis testing. So are we stuck forever with p-values and hypothesis testing? No. There are some changes occurring. For example, the Journal of Basic and Applied Social Psychology completely banned null hypothesis significance testing recently. So you can't get a paper accepted with null hypothesis testing in the journal. There's also a book by Jeff Cumming, who is a statistician professor in psychology, who introduced new statistics, which is all about estimating the effect, not about testing an hypothesis. Finally, a position statement by the American Statistical Association also suggested other approaches, particularly with estimation over testing. For example, using confidence intervals and credibility intervals. So there is a change occurring to other approaches with estimation. So how can we do estimation? A frequently proposed alternative is the use of confidence intervals. But you may wonder what a confidence interval is. What does it mean? Let's try for yourself if you know how to interpret a confidence interval using an example from a recent paper by Higstra and colleagues. Here we have Professor Bumbledolf, who conducts an experiment, analyzes the data, and reports that the 95% confidence interval for the mean ranges from 0.1 to 0.4. Which statement or statements in the slide are correct? Pause the video now and think about it before you press play again. Surprise! They're all incorrect. Were you wrong? Don't worry. The researchers showed that even many professors and people who teach statistics get it wrong. Perhaps you thought, like many others, that the confidence interval represented the range where we would expect the population value to fall. However, this is strictly speaking incorrect, and such conclusions are only allowed with another method to statistical inference, which is called Bayesian analysis. We will discuss this briefly in a second video. This would be the only correct conclusion. If we were to repeat the experiment over and over, then the 95% confidence interval, then 95% of the times the confidence interval contains a true mean value in case of a 95% confidence interval. We don't know if the true mean, population mean, is between 0.1 and 0.4 based on one interval from our experiment. Of course, this correct interpretation of the confidence interval is quite uninformative, as a confidence interval does therefore not provide the answer we would like to know, which is what is the effect in the population. We don't want to know something about the long-run effects. So, Batterham and Hopkins, the developers of Magnitude-Based Inference, however, describe the confidence interval as the range within which the population value is likely to fall, with likely usually referring to a probability of 95%. This is not in line with the frequentist definition of a confidence interval as we discussed in the previous slide, but it is a Bayesian definition, something we will come back to later. So let's try to understand the confidence interval as described in magnitude-based inference. It's pretty straightforward. Let's say that we've done an intervention and found a change in muscle strength of 20 kilo following 4 weeks of training. Based on the mean change found in a sample, we can calculate the confidence intervals of the change. Let's say the confidence interval ranges from -5 to 30 kilo, which in magnitude-based inference means that the difference in the population is likely anywhere between -5 and 30 kilos. So it's the likely range of the population value. So how can we use confidence intervals for statistical inference? Here again we have the null line, with all values greater reflecting an increase in muscle mass in this example, and all values smaller reflecting a decrease in muscle mass. Now we plot the 95% confidence interval. Just to repeat, in magnitude-based inference, the confidence interval represents the range within which we would expect the population value. In null hypothesis significance testing, inference is usually about whether the effect could be zero or null. If the 95% confidence interval includes zero, the effect could be zero and is said to be statistically non-significant. So for the first 95% confidence interval, Would this effect be statistically significant? No, because the population effect could be zero as the confidence interval overlaps the zero or null line. The second confidence interval is a significant increase in muscle mass because it does not contain zero. And the third one is also significant, but is a significant decrease in muscle mass. However, the problem is, although we are using confidence intervals, we are still making dichotomous decisions. For example, it is often concluded in the case of the second interval, yes, it works, or yes, it is effective, or in the first interval, no, it doesn't work, or there is no difference. However, significant is not practically or clinically relevant, as you will see next. This is one of the reasons that has motivated the development of magnitude-based inference. Magnitude-based inference is a relatively new approach, also already from 2006 by Will Hopkins, shown on the left, and Alan Batram, shown on the right. It uses no p-values, but confidence intervals in a Bayesian interpretation in relation to the smallest worldwide change. This is how it works. First, you define a smallest worldwide change, which is a value that will have an impact on performance, health, or injury risk. We will come back later to how to do this. Let's say our smallest worldwide change is 5 kilo. So every increase larger than 5 kilo is beneficial or harmful when we're talking about the effects of intervention, for example, training. Everything smaller is too small to be relevant. Or when we talk about a comparison of groups, every difference larger than 5 kilo will be substantial, and smaller would be too small to be of relevance. When you find an effect, you also compute the confidence intervals for this effect and interpret them in relation to the smallest worldwide change. For example, assume we did an intervention study to see the effects of a training method on changes in muscle strength. We calculate the difference between the control and experimental group and see a mean difference of 9 kilo. Our smallest worldwide change was 5 kilo. The confidence interval ranges from 6 to 12 kilos. So the conclusion is the intervention is clearly beneficial and we should use it, as illustrated here by the first confidence interval. The second confidence interval ranges from 2.5 to 10.5 kilo, and this is also clear. In the worst case scenario, the intervention for the population is trivial. In the best case, it's beneficial. So we'd also use this intervention. And the same for the third interval. In the worst case, it's trivial, and in the best case, it's beneficial. But it's not significant, even though it can be practically relevant. P-values therefore fail here according to Hopkins and Batram. And here we have the fourth interval, and for this one, it depends. In the worst case, it's likely trivial. In the best case, it could still be beneficial. So if it involves minimal effort in terms of time, financial costs, then you could use it. For example, if you could potentially improve your performance by taking 1 pill of vitamin D a week, then this is a minimum effort, which may be worth the effort. For the fifth one, it is clear that the intervention is likely trivial. In other words, the effect is too small to be relevant. You would not use this intervention. However, as you can see here, the p-value shows it's significant. The line, the confidence interval, does not cross the zero line, so it is significant. P-values therefore fail here. And for this one, it's also clear you don't use it. It can be trivial at best and harmful in the worst case, so you don't use it. This one's likely only harmful, so we don't use the intervention. And this one is unclear. If you did a study and report back to the coach or doctor that you find the intervention could work out negative, but also positive, or it could have no effect, then this is of course not very informative. We knew this already before the study. In this case, you need to collect more data. So this slide shows the same idea with areas of benefit, harm, and a trivial area. However, here I've shown the normal distribution with the area under the curve that represents the 95% confidence intervals. In this case, the confidence interval or normal distribution overlaps trivial and beneficial. Now you may wonder, is the intervention more likely to have a trivial or beneficial effect? To answer this, Excel can calculate the probabilities that the true effect is beneficial, trivial, and harmful. So the yellow area reflects the probability that the true effect is beneficial, The orange area reflects the probability that the true effect is trivial, and the red area, almost not visible here, reflects the probability that the effect is harmful. Therefore, per outcome you will get 3 probabilities, and if you have a lot of outcomes, this will result in a lot of numbers. Again, here we see them again. So in papers, you generally want to avoid reporting too much numbers by converting the quantitative statements to qualitative statements using the scale shown here. Let's see an example. A pharma intervention had a probability of 0.1 for a harmful effect, 34.9 for a trivial effect, and 65% for a beneficial effect. You could then report that the intervention possibly had a beneficial effect, because here the 65% is within the range of possibly. This is also an effective way to communicate the findings to a coach, doctor, athlete, or patient who is not interested in hearing a lot of numbers. So this is an example of how you could report the results in a paper. You provide the means, for example, pre-intervention mean, post-intervention mean, the standard deviation, the difference, for example, percentage difference, and a qualitative assessment about the magnitude of the difference and the uncertainty. In the first line, the difference from pre to post is 23.7%, with 90% confidence interval from 9.6 to 39.6. This is very likely a moderate magnitude improvement. We will come back later on how to determine the magnitude of an effect. In the third line, here the difference is 0.3% with a 90% confidence interval from minus 5.6 to 6.6. On average, it is therefore a trivial effect, but it could be substantially decreased and increased. Therefore, this is unclear, but you can still provide an estimate of the most likely probability. In this case, 80% probability for the trivial change. So there are 3 forms of magnitude-based inference: clinical, odds ratio, and non-clinical, also called mechanistic magnitude-based inference. They differ slightly in how you interpret the inferences. You would use the clinical inferences if benefit and harm are relevant. For example, if you investigate the effects of a high-fat diet on 5-kilometer running performance, it could harm the performance, but it could also be beneficial. Similarly, if you investigate the effects of a specific training method on the incidence and severity of injury, it could harm the individuals by causing more injuries, or it could be beneficial by resulting in less injuries. But it does not only apply to sports. Also in a medical setting where you would be interested in the effects of a specific chemotherapy on mortality rate in cancer patients, this would apply. In all these cases, you would use an intervention if it had at least some probability of being effective, but also you want to be sure you don't do any harm. Hopkins has suggested that you could therefore use a probability of more than 25% for possibly beneficial and a probability of smaller than 0.5% to make sure that it is most unlikely to do any harm. So in other words, if there is a if the probability for benefit is higher than 25%, but the probability of harm is higher than 0.5%, the effect is said to be unclear. You would like to use it, but you dare not because the risk of harm is too high. However, if the probability of benefit is high, for example 80%, you could accept a higher risk of harm, for example 5%. Hopkins has suggested that in such a case, the odds of benefit to the odds of harm should be at least 66. This method is called odds ratio magnitude-based inference. So far, clinical and odds ratio magnitude-based inference. Non-clinical or mechanistic magnitude-based inference is used when you compare groups when there is no obvious relation to benefit or harm. For example, a comparison of length between males and females. Here, risk of harm is no problem, so you would accept a higher risk. Here are the 3 forms of magnitude-based inference shown with confidence intervals. Above is an intervention study which shows a probability of 2% for harm, 33% for trivial, and 65% for beneficial effect. Since the cutoff for clinical magnitude-based inference was less than 0.5% for a harmful effect, this effect is unclear, even though there is also quite a probability for the effect to be beneficial. You would like to use intervention, but you don't want to take the risk. However, if you use the odds ratio magnitude-based inference, as shown here in the second graph, you could decide to use an intervention that showed a higher risk of harm if the risk of benefit was also higher, as long as the odds of benefit to harm are higher than 66. In this example, the probability for harm is 4%, as shown here. But the probability for benefit is 73%. You could decide to use this as a probability for benefit outweighs the risk of harm. Finally, when we take exactly the same effect as in clinical magnitude-based inference in the first example, in non-clinical magnitude-based inference, this would be a clear effect because the probability of harm should be less than 5% and not less than 0.5%. However, here we are also not talking about harm and benefit, but about, for example, smaller and larger. For example, when we compare males and females on height, as I previously mentioned. Harm and benefit do not apply. Males would, for example, on average be clearly larger than females in this case. So we have been talking quite a bit on the smallest worldwide change. Of course, we need to know the smallest worldwide change so we can say whether an effect is beneficial, harmful, or trivial. For an effect to be clinically or practically relevant, it has to have an effect on performance, injury risk, or health. But how do we determine the smallest worldwide change? In null hypothesis significance testing, we also need to know this, as it is required for sample size. The sample size needs to be large enough to detect the smallest worldwide change 80% of the time. So you also need the smallest worldwide change. So how do you currently determine the smallest worldwide change in your studies if you are a researcher? Or how do you decide which change in performance is relevant for your athletes if you are a coach? Pause the video and think about it for a second. So there are several ways to determine the smallest worldwide change, and the most appropriate method depends on the data. For example, for elite solo athletes' performances with modeling by Hopkins, it has been found that an enhancement of 0.3 times the variability is required to increase the chance of winning one gold medal for every 10 competitions. In other situations, there is no direct relationship between a change in performance on a test and actual sport performance or health or injury risk. For example, if a soccer player increases his sprinting speed, this does not directly result in a higher chance of winning the match. Therefore, in these cases, it has been suggested that the smallest worldwide change can be determined using standardization, multiplying the between subject standard deviation by 0.2. Of course, it would be best to have actual data as the smallest worldwide change. For example, a situation where we know that a 5 centimeter improvement in jump performance will directly increase our number of won matches. But these data are not always available. In this case, we can therefore use standardization. For example, in team sport athletes, as I mentioned, there is no direct relationship between an improvement in their jump height due to training and winning more matches. Therefore, we don't know what change is relevant. We can therefore determine the smallest worldwide change by expressing the difference or change in the mean as a fraction of the between subject standard deviation. The smallest worldwide change is usually considered to be 0.2 standard deviations. Let's see an example. Here we have the bar graphs showing the mean. Here it represents the mean strength of a group pre and post intervention, with the arrow bar here representing one standard deviation. From the bar graphs, you would probably say that the change is really small difference between the graphs, between the bars. If you look at the normal distributions here, you can also see that the change in the mean, so the overlap between the graphs, is too small to be of relevance. The vertical red line is almost the same as the blue vertical line here, which indicate the mean change. The post-intervention mean has moved only 1/10 of a standard deviation. So here the blue lines represent standard deviation. So 1 standard deviation, 2 standard deviations, 3 standard deviations. You can see here the red line has moved up only 1/10 of a standard deviation. In the right figure here, we can see a very large effect. The mean has changed. So the red line here has changed 1, 2, 3 standard deviations, and that would then be a large effect. In the table above here, you can see what the cutoffs are for deciding when something is large, small, etc. So here we have very large, then the change should be between 2 and 4 standard deviations. And indeed, as I showed here, we have 1, 2, 3 standard deviations of a change. So now we know approximately how magnitude-based inference works. What I personally like about magnitude-based inference is that it allows a much more nuanced and informative conclusions than null hypothesis significance testing, and is also much more intuitive. Magnitude-based inference conclusions follow the uncertainty in the data. When the confidence interval is entirely in the beneficial area, as shown by the first confidence interval here, the effect is most likely beneficial. However, when a small part is in the trivial area, as shown in the second interval, we are less certain that the effect is beneficial, as it could also be trivial, and it is therefore not most likely, but just likely beneficial. In the third interval, the probability for a trivial effect is even larger, and the qualitative statement changes from likely to possibly. So again, we're less certain about the effect. So the conclusions in magnitude-based inference follow the uncertainty in the data. With null hypothesis testing, there are just two conclusions possible. It is significant or it isn't. And you can see here there's a 180-degree change in the conclusions from the second to the third confidence interval. Of course, with null hypothesis testing, some people do something like it is highly significant with a p-value of smaller than 0.001 and significant with the p-value of 0.5. But above 0.5, you get many weird conclusions, like very narrowly missed significance. And you can, if you're interested, find more interesting examples at the link below here. So if you're interested in using magnitude-based inference, you can go to the website sportsci.org and download the freely available spreadsheet, which do most of the calculations for you. However, magnitude-based inference has also been criticized, and in the second video I will discuss some of the criticisms on magnitude-based inference. I strongly encourage you to watch also the second video to form your own opinion on which method you should use to analyze the findings of your study.